Hello again, welcome back, and let us now finish the cyclic course by talking about how to actually implement coding and decoding device. So the logic now should be clear that we perform division, we find the reminder, and if this reminder at the decoder side is not 0, the specific value of this reminder can point us to the position of the error, which then needs to be inverted. Yes. Now the only thing is how to put that together into the working schematic. So from computer course, you should know already that. Okay, wait a minute, please. Have some problems with Epic Pen. That from computer course, you should already know how division and multiplication operations are implemented in computers. So basically, we have shifting operations, and for that reason we use some memory or registers or flip-flops, and addition operation. In our particular case, we are going to use specific addition by modulus 2, but in real multiplication algorithm and division algorithm, the addition is not modulus, it's classical addition, yes. But in our particular case, because we are working with Galois field 2 coefficients, we are using XOR rather than simple addition, which makes it more simple, yes. Because as you know, simple addition, for example, if we make simple binary addition like this, can result in carry bits and potentially in overflow. Yes, so here we have 0, we have 1 carry bit here, so 1 plus 1 and carry 1 is actually 1. Again, we generate a carry bit, which is then put here as a carry bit and generate 0, 1 more carry bit here, and accordingly here. So this is classical addition, and this is XOR addition. XOR addition doesn't change the number of bits. So here we have 0, 0, 1, and 0. The result is different, and there is no overflow. Yes. So for that reason, it's a much simpler. Now, depending on if we are working in encoder or decoder, we will need different amount of time to calculate the reminder. Because, well, basically, during the encoding process, we only have K symbols. Yes. And all the others are appended as R zeros, yes, which are already known and can be considered in schematic operation previously, yes. For decoding, we will need to test all M symbols, and this will accordingly ask from us to perform M tacts division, yes. So this means for encoder, we are going to use one schematic, and for decoder, a little bit modified schematic. So yes, let us see the first encoding device. The generalized divider schematic for encoder looks like this. So basically we are having shift register made from these flip-flops, that type flip-flops. Yes, and shift register basically operates like this, yes, that you have, for example, symbol A1, which is recorded into this, and previous value like B0, for example, goes to here. Previous value like B-1 goes to here, and so forth. So basically, each new data recorded into the first flip-flop then shifts out remaining data in the entire register. So at the output, we'll have B-2. Yes, so this is the classical shift register made from flip-flops. Between these flip-flops, however, we may or may not have XOR elements. So how do we know if we need XOR element here or we do not? For that reason, we need to check our generator polynomial. So basically, this represents G0 input, this is G1 input, this is G2 input, and so forth. So if you are having this G1 in your generator polynomial as 1, then you need this XOR. If G1 is 0, then this XOR is omitted. Let us see a specific example of this schematic for our particular generator polynomial represented by this expression. So in our particular generator polynomial, G1 is 1. Yes, you can see z at the power of 1 in this polynomial. G2 is 0 because there is no z squared in this polynomial. Yes, so G1 has XOR element and G2 has no XOR element. Yes, no XOR. So we put these XORs only before these flip-flops, depending on the generator polynomial. So again, let us take, for example, just for example, some, I don't know, z power of 6 plus z power of 4 plus z power of 2 plus z power of 1 plus z. For example, this polynomial, yes? So where will we need to put these XOR elements? So I'm going to need 6 flip-flops because I have z power of 6, so that will give me 6 triggers or 6 D-type flip-flops. Yes, so total number of these flip-flops is R. In my particular case, R is 3, so 1, 2, 3. That would be 5, and that would be 6. Now I need to decide where do I need to put XOR. So this XOR is present always. Yes, so regardless of your generator polynomial, because it adds together Z6 and 1. Yes, so Z0 basically. Yes, so this is always present in any generator polynomial, and the remaining depends on the these powers. Yes, so we have Z, so that means we need XOR here. We have Z squared, that means we need XOR here. Yes, we also, so we don't have Z3, so no XOR after the third. We have XOR here, Z4, so after this is the fourth trigger, yes, fourth flip-flop. After the fourth, we also need XOR. We don't have Z5, meaning that we will not put XOR here. So basically, we put XOR after each. So this is Z1, this is Z2, and this is Z4, right? If they are present after these flip-flops, we put XOR. So hopefully, this is clear how to generate this part, yes? Basically, number of flip-flops is the maximum degree of generator polynomial, and each XOR accordingly represented by these flip-flops. So here we have Z, we have XOR, here we have Z3, we have XOR, yes? Now, what is the other part? What is this part? So basically, encoding device needs not only find this reminder, but actually combine your data and this reminder into the single code word. So here we have data. Here we'll have at the output code word. So here is the in, here is the out. Yes. And based on this data, we must find reminder, which needs to be added to our data and make the code word. So code word is data and reminder. Yes. So how does this work? This works very simple. This schematic will calculate reminder in k time intervals, k tacts. In our particular case, 4 tacts. Yes. And during this process, during the calculation of the reminder, the switch is connected to the point 2. After these 4 tacts, starting with 5th, yes, this switch is reconnected to here. this way, it will allow this reminder to be read to the output. Yes. So basically, first 4 tacts, our data is sent to the output, and here we have 0. So basically, data plus 0 doesn't change anything. Yes, data is the same. And during the intervals 5 to 7, our data will be zeros, which we have appended. As you remember, before division, we need to append at the end zeros. So these zeros will be added together with this reminder. So this will output a reminder. So basically, the idea is very simple. First 4 intervals, data is duplicated at the output, and at the same time, simultaneously, this schematic calculates reminder. Last 3 intervals, we read this reminder and append it at the end of the code word. So this way, our schematic works. Actually, I have uploaded example of tag-by-tag operation of this schematic for some specific code word. So you may familiarize yourself with it. Please note, however, that before activating this device, we need to set all triggers to 0. So we need to reset all the flip-flops. Yes, this can be done by using special input. It isn't marked here, but usually they have reset input, yes, on which you can send signal, and it will accordingly clear the contents of this memory cell. Yes, because basically flip-flop is actually a memory cell for 1 bit. And here you can see the process of generating data. So basically, first 4 intervals, as you can see, we have sent our data to the output, and at the same time we have calculated this reminder, and the next 3 intervals, this reminder will be read one by one after each tact. So during between 4th and 5th time interval, you can see that we have changed this switch. Yes, and basically we read this interval. So in order to make it a little bit easier for you, let me explain how this schematic actually works. So we have 3 flip-flops and 2 XORs. Well, I will draw these XORs like no, sorry. This XOR needs to be in between. Yes, so basically XOR and XOR here as well. Yes, so this is XOR and this is also XOR. So this XOR has this feedback connection, and all the others are connected like this. So initially our flip-flops contain 0. Well, then we get some data bit. For example, let it be 1, for example, yes. So what happens next time interval? So what happens is that these zeros are shifted out. So basically, they go from inside to the outputs here. This one, this one goes here, and this one goes here. So the contents of this flip-flop is read. Yes, reading of these flip-flops. So this XOR generates 1, which goes through this feedback and adds to the input of this flip-flop. So this way, this 0 plus 1 is recorded to here as 1. Yes, it's at the same time it's recorded inside here also as 1, and this 0 is recorded here as 0. Yes, so basically next symbol comes here, for example 0, and the whole process is again repeated. So everything is sent to the outputs. This XOR generates feedback, and this feedback recorded here, and here feedback records with the output of the previous state of this flip-flop. So this process continues for 4 intervals, and that gives us a reminder. Yes, so basically if we check, yes, this is actually correct reminder. So 1 0 0 1, append 3 zeros and divide with the generator polynomial, which is Z3 plus z plus 1. I don't have z2, yes? So let me divide it one more time to practice it, yes? Because in your course project you will need to perform this division. Sorry, I didn't intend to write down this just yet. So I take next symbol. I don't have 4 symbols, so I put 0 here. Take next symbol, so I can divide it. Yes, I take last symbol, and I cannot continue because I don't have any more symbols, and I cannot divide this either. So remainder is indeed 1, 1, 0. And as you can see, after 4 intervals, we have this 1, 1, 0. Please be aware that it's in mirror, yes, because here we have serial data transmission, meaning that we send one symbol during one interval, and accordingly this will go out first, this will go out second, and this will go out last. And this will form the correct sequence of 1, 1, 0. Yes, so for that reason, this needs to be in mirror, and you need to consider that. Okay, then. Encoding device is, well, maybe its operating logics are not very simple, but schematic is rather simple, yes? You only have flip-flops and multiple XOR, and this switch, which is reconnected after k time intervals. So the logics, maybe the operation principle maybe not so simple, yes, but the design logic is quite simple and pretty straightforward. So let us see then how can we decode. So for decoding, we need also to calculate remainder. However, now we'll have to calculate all M symbols because now we have non-zero control symbols, yes, at the end of our code word, and basically we need to divide everything. So the only difference between encoding and decoding divider schematic is that this XOR, which was previously here, yes, is now moved forward to this position. Yes, so if we compare this schematic and this schematic, well, we also don't have this part, but this XOR now is put here. Yes, so that is all the difference. So in our particular case, for our generator polynomial z3, z plus 1, we'll have this here XOR, and this XOR is as usually after z1. So this is z2, we don't have XOR here, and this is z3, we don't have XOR here because we already have this XOR. Well, basically, you need to understand that XOR has 2 inputs, so we need to calculate actually z3 plus z plus 1. Here comes z3, so here we have z3, here comes 1, so this is z3 plus 1, and this XOR accordingly adds z1. Yes. So basically, altogether, it's generating this polynomial. It's not very pretty that simple, straightforward, but the idea basically is this way. So again, this is just a schematic that finds division. This is not a decoder. So after 7 time intervals, we'll have a reminder inside this. So for example, if we have no errors, then after 7 time intervals, we'll have 0, 0, 0. This means no error. If we have error in the last bit position, then we are going to have 1, 0, 0 reminder. Oh, sorry, 0, 0, 1, like this. So this is if we have error in position at the last bit, yes. And as I have said, you need to be aware that it's in mirror, yes, 0, 0, 1. So what do we do then? And how do we make the correction of error if we have this reminder already known? So it depends on if we like to find error or if we'd like to correct error. So of course, it's more difficult to correct error than just to alert that we have error. But let us first see the simpler solution with finding error only. So error detection only, simpler case, yes. For that reason, we are going to need this dividing schematic, which we already have discussed. So this is this schematic, yes. And basically some kind of error detector, which generates the signal that we have an error. And in addition, we also need a memory to store our data before we find out if it has an error. Because if we don't use this buffer register, then the data goes out. It takes from us m equal to 7 time intervals to find if we have error. But by that time, data will be gone, and when we alert that we have error, it will be too late. Yes, so for that reason, we need to actually delay this data, put it in queue, yes, to wait for 7 time intervals, 7 time intervals, yes, and during this time, while we fill this shift register with data, we calculate the syndrome. And if the syndrome is 0, then it's okay to read this data from this buffer register. If it's not 0, then we have error and we need to do some additional actions. Yes, maybe request retransmission of this block and so forth. So what about this error detector? How do we make this signal? Well, it's actually pretty simple. Yes. Okay, so what we have here is the more detailed version of this logical structure. So this is the buffer register, which is basically shift register of 7 m equals 7 flip-flops. Yes, 1, 2, 3, 4, 5, 7, 6, 7. Yes, they are connected output to the input, and basically each time interval, for example, we get here 1, and the first time interval is here, at the second time interval it's go here, third interval here, fourth interval here, fifth interval here, sixth here, seventh here, eighth interval it will go out. So basically it takes 7 time intervals to get from input to this position, and at the 8th it will go out. At that time we already know if we have error or we don't. So this is basically some delay line to actually wait for calculation of the syndrome. Now this yellow denoted part is actually the schematic of the divider. So this is basically our this schematic, yes, which finds the reminder, and it takes 7 time intervals to do that. Now, if we have this reminder as 0, yes, 0, 0, 0, then we have no error and everything is okay. Yes, and accordingly, how do we know that it's okay? Well, we use simple OR operation. Please don't mind this not inversion, it's incorrect. It's just a simple without inversion OR operation. Yes, OR operation. Basically, if any of these contents will be 1, for example, like this, then OR will produce at the output 1, which is the signal of the error. Yes, accordingly, it will produce 0 only in a single case. When all the inputs are 0, then OR function will get us 0, and accordingly this is correct. Yes. Well, why do we have inversion here? Is because it's connected with reset input of these flip-flops. Yes. So reset will happen only if here we have 0. Yes, so if we have here 0, it will reset. However, we don't want to reset for zeros. Yes, because it's okay. We don't need to reset because we don't have error. So we reset only if we have error. If we have error, we reset it and then send the signal to retransmit, for example. Yes, so for that reason, I have put an inversion here to convert this 0 into 1. Yes, so basically logic now is inverse. Yes, if 1, it's okay. If 0, it's an error. Yes, so 1 does not reset these flip-flops because it's reset by 0, and 0, which can happen only if any of these elements is 1, for example, this way, or this way, or even this way, all of them will produce at the output of this NOR gate, yes, symbol 0, which will then reset all flip-flops, erase the received data, and will request retransmission. We cannot correct error with this schematic, but let us see improved version, which will have two divider schematics, tax divider number 1 and tax divider number 2, and error detector, which accordingly performs correction. Yes, so how does this operate? So we still need to wait for all data to be tested for errors, yes, before we read this data. In the same time, this divider calculates a reminder, yes. So once the reminder is calculated, we know if we have errors or we don't. However, it takes time to read this buffer register. Yes, basically 7 more time. Well, not 7, but m more time intervals to read all the data. In that time, new next code word will be arriving for which we will need to perform the division. So for that reason, we need a copy of this schematic, which will be capable for searching for error position at the time when the first schematic will start processing next code word. Yes, because you need to realize that this is actually a communication system and data comes without interruption. So we have code word 1, code word 2, code word 3, and so forth, and without stops. Yes, so this needs to be like some kind of conveyor which basically checks for error and takes next code word, checks for error, next word, and so forth, without interruptions, without delays, and so forth. So yes, for that reason, first schematic will find the reminder, and the second schematic, if this reminder is not 0, we accordingly generate correct error signal, which will invert the symbol at the corresponding position. And let us, well, buffer register doesn't really change, it's the same. Divider schematics are the same. So the question is, how do we correct the error? That is the only question. Yes. Oh, unfortunately, logic is quite convoluted, and next lecture beginning, next week, yes, lecture beginning, I will show you some graphical material which will hopefully help you to understand better how this error correction process is performed in this uninterrupted operation with the schematic. But if we talk about basic principle, then the idea is that we need to search for this specific syndrome. Yes, this is called a dedicated syndrome. Dedicated. And it is the syndrome of the error in the first position of the code word. Yes, basically, why is it so? The idea is quite simple. Consider that we have this code word, which was here, yes, 10011110, and it will accordingly arrive in mirrored type, yes, 110. Sorry, was it correctly? Yes, 110. So it will then be recorded in this buffer register. So it will take 7 time intervals to record this completely in this buffer register. So that takes 7 time intervals. During these 7 time intervals, we'll calculate the error, the syndrome. Yes, and for simplicity, let us introduce the error in this first symbol. So now we'll have here not 0, not 1, but 0. So basically, this is the error. Yes. So imagine that we have error happened here. This should produce in this divider the syndrome 101. Yes. So this will give us 1, 0, 1, which is copied to this schematic. And accordingly, when we read data at the next takt, this is going out. Yes. And this is our only opportunity to actually correct the symbol, because at the 90, we will be reading this symbol and this will be already gone. Yes, and now we need to correct error when we read data. So we read this 0, and this error detector generates symbol 1, which accordingly inverts this 0 into 1. Yes. Now imagine the situation that we have error not in the first position, but in the second position. Here. Yes, and accordingly this will be 1, and this will be still 1. So we need to. So again, we have 8 time interval. We read this symbol 1. It doesn't have any error, so we should not correct it. It should go as 1. Then at the time interval 9, we will be reading this symbol, and at this time we need this correction signal. Yes, so it should be inverted and received as 0. And the trick is that actually the reminder for error in this position was 111. Yes, 111. So at the takt 8, this reminder will be 111, which doesn't correct any errors, because only reminder 101 is when we trigger the correction. Yes. So how do we go from this reminder to this reminder? Actually, it's basically next in the table. Yes. So we basically go from this reminder to this by continuing division. So for that reason, we need that second divider schematic. Yes. And similarly, if we have error in this symbol, then we'll get this reminder, and it will take at the 8th takt this syndrome, 9th takt this syndrome, 10th takt this syndrome, 11 this, 12 this, 13 this, and 14 this. By that time, a 7 symbol will be read from buffer register, and we will have the signal to correct error. Yes, so the logic is quite complicated, I agree, but it works. Yes, and basically the secondary divider is converting the syndrome to the next syndrome until we get to the last syndrome. Once we get this last syndrome, we need to perform correction. So the only question is, how do we implement this error detector? Quite simple way. We need a schematic, yes, basically conjunction or disjunction. It depends up to you. You could use AND element, you can use OR element, but in my example, I have used AND element. So AND element produces one output only and only if all the inputs are ones. 1, 1, and 1. Yes, only in that case it will produce 1. We need to produce 1, however, for this case. For that reason, we should take the middle one with inversion, with NOT gate. Yes, so after this inversion, it will be converted to 1, and this way it works like this. Furthermore, any flip-flop has 2 outputs. Yes, basically, you can see it here. Flip-flop output, direct output, and inverse output. So basically, if the direct output we have 1, at the inverse we will have 0. So it really comes down to correct connection of these flip-flop outputs. So the entire schematic will look like follow. This is shift register. In previous schematic, it was drawn like a series of multiple flip-flops, but there are also components in drawing software which accordingly, well, basically draw it as a single component. Yes, keep in mind that if you have m equal to 31, for example, then you will need 31 flip-flop, or accordingly you can connect 4 such registers in a row. Yes, so here we have input, here we have multiple outputs. Yes, so we need delay of 7 time intervals. No, here is just this serial, yes? So we basically connect it, and connect it. Yes, so you need to connect them one by one, and that will give you total of 32 time intervals. Yes, and because of that, for the last one, we need to actually connect to Q6. Yes, Q6 to get 31, because this QS is actually the same as Q7. Okay, so for this shift register, I think it's clear. This divider is exactly the same as this. They are same divider schematics. Yes, this is just an M tacts interval dividing schematic, which is this one. And here is error detector. Yes, so basically error detector is AND function, which is connected so that we read from these flip-flops our dedicated syndrome. So basically here we take direct output because we should consider 1. Here we take inverse output, yes, so that this 0 is converted into 1, and here we take direct output, so it's also 1. So this way 1, 1, and here we also connect to 1, basically voltage of 1, for example 5 volts. Because in my particular case, I have 4 input AND gate, yes, and I need to send 1 to each of them. This is always 1, and these 3 are read from these flip-flops. First and third is read from direct output, and the last is read from inverse. Similarly, if, for example, you would have, yes, you would have dedicated syndrome this one, yes, then you would need to consider that here we have 0. Don't forget that it's in mirror. Yes. And then we would take direct output here, and inverse output here. Yes, like this. So it's quite simple to make this decoder. Now this decoder through XOR gate is connected to the output. Yes, so here we have output from shift register. Here we have this correction signal. Here we have XOR, which performs correction of the error, and accordingly at the same time this is connected to the input of the second schematic. Yes, because we need to send something here, and basically this signal will reset these flip-flops. Yes, so this is schematic of the Hamming cyclic code, which performs correction of the error. And here we can see switches which are activated between actually 7 and 8 time intervals. Once we have this reminder calculated, it is copied into these flip-flops. Yes, so that's the logic of the schematic, and you will need to draw for your case in your course project this schematic. But again, as I said, I will next week start with some easier to understand graphical representation, some maybe animation, I don't know, maybe video. I will design to show you this entire process of how this code word goes through this schematic and when it is corrected in different cases, in different positions of error. So for the lecture part, that would be today all. Do you have any questions? So currently I see no questions, but if you do.
Yes, it is not on the course, it is in the project. What is the date for the work? I think we need to do some part of the
course project, yes.
course project.
Yes.
But when? What is the date?
So
the last day.
So the data which you need to take as information part is your name, surname converted into binary form, yes, and you basically do it the same way as for group code, which we have discussed last lecture. And actually right now, after a short break, Mr. Chen will show you all the process which you need to go through for your course project. Yes, so basically this was lecture, and I have shown how to draw schematics, but Mr. Chen will now show you how to solve this task 5 for cyclic codes. Yes. So basically encoding, decoding without errors, with one error, and so forth. So that will be explained in after short break in a few minutes to you. Yes.
Okay.
So then let us make a short break and continue at 11:05, and Mr. Chen will then show you how to work with your course project for cyclic codes. Yes.